All right, so in this video, we're going to be looking at how to choose which method of solving systems of linear inequations to use in a particular problem. Now, we learn several of these methods as we are solving, as we are learning to solve systems. We can solve by substitution, we can solve by elimination, and we can solve by graphing. And all of these methods generally work quite well, although they do take some practice in order to get used to each one of them and to know, to feel comfortable with them. As you are learning, particularly when you need to make sure that the solution is correct, I mean, it's often typical to choose one particular method and kind of stick with it until you get more comfortable with some of the other methods. And that's fine. But ultimately, we want to be masters of all of our different solution methods. And so there are certain times where one method might be a little bit easier to use than another, assuming that we have equal levels of comfort. And so we're going to go through each of our solution methods and kind of identify which of the methods is appropriate in a given example. Now, in this case, if we're using the solving systems of equations by graphing, we're going to use, here's our example system. And if we're going to go ahead and solve this by graphing, our calculator, if we're using our TI, for instance, we're going to need to solve for y. If we are using something online like Desmos or something like that, then we may not have to solve for y. We can just put the system in the way that it is. But if we're using our TI calculator, we would need to solve for y. And so we're going to do that by, in this first equation, we're going to move our x over to the other side, and then we'll have y equals negative x minus 2. And in this case, we have a little bit more algebra to do. If we move the 3x over, and then we divide by negative 4, we end up with 3/4 x minus 2. And so we're going to enter the first equation into our y1 screen on our TI calculator, and the second equation into y2. And when you do that, you get 2 lines on your graph. And then you're going to identify the point on the graph where the 2 lines cross each other, which in this case, you can see clearly is the point 0, negative 2. Now, potential advantages of solving a system by graphing would be that if the equations are already solved for y, they can go directly into your calculator. If the equations have integer solutions for both variables, then they may be particularly easy to read off the graph, particularly if you have grid lines on the graphing program that you're using. If you are going to round your answer anyway, then your graphing program has a feature to find the intersection for you, and you can get the required accuracy directly from the program without doing any algebra. So this may be appropriate if you have like weird square roots or things like that as your coefficients. You're not necessarily going to want to express your solution as a very complicated expression. And so a decimal solution might be appropriate. Or if you already have decimals in the problem, then you're expecting to get decimals back out of it. And so again, that may be appropriate. If your system of equations is very complicated with a lot of fractions, you may not need to fully reduce all of the algebra manually in order to get this particular graphing method to work. And if the system is inconsistent, the graph of 2 parallel lines is quite distinct from each other. And then if this method will work for not only a 2-variable problem, but it will also work for nonlinear problems that you may encounter in other courses. Now, potential disadvantages are if the equations are not already solved for y, as we saw earlier, then you have to do this algebra first. If you don't reduce your fractions, then you'll need to be very careful about how you put parentheses into the problem. If you leave out things or you don't put parentheses where they need to go, then the equation that you get will not be correct. So for instance, not reducing my y2 equation in the previous example, I would have had to enter with the numerator surrounded by parentheses, and then divide by 4. If I had forgotten to put parentheses around my numerator, then only the 8 would have been divided by the -4 and not the 3 as well. And that would have given me the wrong line and therefore the wrong solution. If you need exact answers, the fractions that result at an intersection are typically uncommon, like if they're dividing by 19 or something, then your calculator may not be able to give you enough decimal places to make the conversion back to fractions by copying that decimal onto the main screen. If it's like a quarter or something, then that's a nice round decimal, and that will easily convert to a fraction on the main screen. But again, not if it's something weird that you could get by doing the algebra, but not if you don't have all the 10 decimal places you need for the calculator to recognize the fraction expansion. You may graph 2 equations and only see 1 equation on the screen. You have to be careful for a couple of things. It may be that the lines are graphing onto the same line, and then that's why you only see 1 line. That solution would be in an infinite set of solutions. On the other hand, it could be that it's simply not showing up because it's out of the range on your window. And so you may need to zoom out in order to be able to see if that's the case, if it's actually on the screen, but just off the window, or if it's just not there at all because it's on top of the other line. You may also need to adjust the window to find where the intersection is. And so that is another, if you use the intersection function, if it's not on your screen, you may not actually get the calculator to find it, in which case you may falsely interpret that as actually the second line not being there, or there being no intersection, or being that infinite set of solutions, when in fact that is not the case. And if there are more than 2 variables, or certainly 3 variables, then obviously we don't have a 3-dimensional graphing program on the TI, and so we can't see in 4 dimensions anyway, and so we can't solve it by this method. So this is limited to 2-variable problems. Now, our second solution method is substitution. And again, we're going to look at the same set of equations, and we're going to use the substitution method to solve this. Now, the way substitution works is you take one of your equations, you solve for one of the variables in one of those equations, and then you substitute that in for that variable in the second equation, so that what you end up with is a system that has only a single equation that has only one variable in it. So the strategy for this kind of thing, again, my main recommendation would be if one of your equations has a variable where the coefficient is 1 or -1, then that would be a good problem to use substitution on. And so that's what we have here. So I'm going to take this first equation and solve it for y. So step 1 is the same thing we saw in the previous graphing step. We move x over and we get y equals to -x minus 2. But instead of solving the second equation for y, we're going to plug this substitution for y into our second equation. So I had 3x minus 4y equals 8. And so when I plug in for y, this is going to be 3x minus 4. Here's my replacement for y equals 8. And then I continue simplifying. My like terms, 3x and 4x add to 7. The 8's cancel, and I end up with x equals 0. And then I plug my 0 into my y equation for x in order to obtain y. And this matches the solution that we obtained from the graph. Now, potential advantages of solving systems by substitution. Again, if at least one of the variables in the equation has a coefficient that is 1 or -1, you can avoid introducing any fractions into your algebra, which makes the algebra go faster. This method will work on systems with any number of variables and on both linear and nonlinear systems. So if you had an x squared or something like that, you could still use this procedure to solve those problems. You only need to manipulate one equation with two variables and just long enough to solve for one of those variables. And then substitution reduces the second equation to a single variable, so it's easier to do the algebra on it. Typically, substitution is the first algebraic method that we learn, so students often feel that it's the one they're most comfortable with, and it is capable of giving exact answers when exact answers are required. Now, some potential disadvantages of using substitution. If none of the variables in either of your equations has a 1 or a -1 coefficient, then you're going to have to work with fractions as you go through solving. So there's just no way around it. You're just going to have to deal with adding and subtracting and multiplying fractions. When there are more than two variables, this procedure can be tedious. You have to basically eliminate one variable at a time. You solve, in a 3-variable case, you will solve one equation for one of the variables. Then you'll make that substitution into the two remaining equations to reduce them from 3 variables to 2 variables. And then you will repeat the substitution process on one of the two remaining equations, solve for one of the variables in one of those equations, and then substitute again into the last equation to make that one variable. And then you can go ahead and solve for one variable and then go backwards to your 2-variable equation to get the second variable, and then all the way back to your first equation to get the final variable. Again, it can be tedious, and the more variables you have, the longer this procedure is. Sometimes you'll get systems with 3 variables where one of the equations doesn't have all of the variables, and so maybe that's more appropriate. But typically, when you do problems with 3 variables and you use substitution, you're inevitably going to get a lot of fractions and crazy stuff that you're going to have to work with, because it's very hard to get systems where the variables remain a coefficient of 1 as you start manipulating them. And it is often an error that students make. Well, they'll solve for one variable and then they'll forget that they're dealing with a 2-variable problem, and they'll simply stop and forget to solve for the second equation. So it may seem like you're done before you're actually done. And then our third method is elimination by addition. And so typically this method is most commonly used when both of your equations are in standard form. And the strategy here is going to be to multiply one of your equations by something so that when you add the two equations together, one of the variables drops out. Now, if you have equations where one of the variables already has an opposite sign, then that's usually the coefficient or the variable that I like to eliminate. That is not a requirement for this process, but that is, if I can get that, I prefer that, because then I don't have to worry about using extra minus signs. But you don't have to do that. You can just always try to solve for eliminate x or something like that. But in this case, my initial equation was x plus y, and my second equation was 3x minus 4y. So the y's were opposite signs. And so that was the one that I decided, okay, I'm going to eliminate the y's. And I got the coefficients to match, but the opposite signs, by simply multiplying the top equation by 4. So before I had x plus y is equal to -2. When I multiply everything by 4, I get 4x plus 4y is equal to -8. So you have to remember to multiply the whole equation, both sides of it, by 4. And now if I add vertically, the 4y and the -4y are going to cancel each other, so you're going to get 0. And so you're going to end up with 4x and 3x is 7x. And on this side, -8 and 8 is going to give me 0. and I'm back to an equation with a single variable, and I can solve for that as x equals 0, and then I can plug x equals 0 into either of the two original equations in order to get my second solution. So if I plug it into my original first equation, 0 plus y is -2, which gives me y is -2, and I have that same solution that I had earlier. Now, potential advantages of solving systems by elimination. The entire procedure can be done by only working with whole numbers. So if you don't have coefficients where one of them is a coefficient of 1 or -1, where you could substitution would introduce fractions into the problem. You don't have to worry about introducing fractions into the problem when you're using elimination. You can just avoid them altogether and just modify one or both equations until you can get them to match up. This method is a little easier than some others for working with systems of equations with more than two variables. And it can be generalized to another method of solving equations involving matrices that you will learn later on in algebra. And the algebra after the elimination step will be further along than at the same point in the substitution procedure. So fewer steps left, slightly more efficient. And like substitution, it can provide exact answers when they are needed. Now, some disadvantages. Sometimes students may find it confusing to match coefficients when both equations need to be modified. So if you have something like 2 and 3 in your two equations, like what do you multiply them by? Well, typically you would have to multiply the first one by 3 and the second one also by 2 in order to get those both of those coefficients to be 6. And then, of course, you don't want them to be the same sign. You need them to be opposite signs. So one of those would have to be flipped to a negative. And so sometimes students can find that confusing. And it's typically the last of the three methods learned. And so it is the newest, and so the one that they're least familiar with. If you commonly make errors when distributing negatives, you may need to be especially careful when you change signs using elimination, because of not changing all of the signs will affect your outcome. In order to avoid working with fractions, you may be required to work with and reduce very large numbers, so that is a potential disadvantage. And so just some general sort of notes on how to choose the best method. If the system already has both equations solved for y, and there are only two variables, graphing is a good first choice. Fall back on substitution if you can't get an exact solution from the calculator and need one. If the system of equations requires a lot of algebra to simplify each equation, you may use graphing to avoid reducing as long as you can solve for y without too much difficulty. If the system has at least one equation solved for either variable, you can use substitution. So maybe you have one equation solved for y, but not the other one. If a system with more than two variables has any equations with fewer than the full number of variables, say you have a system with 3 variables, but one or more of the equations has 2 or only 1 variable, then this system will be easier than usual for substitution. So again, use your best judgment. If a system of equations has at least one variable with a coefficient of 1 or -1, substitution will be good by solving for that variable that has that one coefficient. If none of the coefficients in the equation is 1 or -1, use elimination. If you have large numbers of variables, use elimination, except possibly for certain special cases. So as noted above, if you have an equation, a system with 3 variables, but one of the equations is just x equals 2, then you can just use substitution to simplify the problem and then reassess. In problems where you are allowed to choose your own method, do not be afraid to switch methods in the middle of a problem. If you see an easy way to substitute for the first step, but then obtain equations that have no coefficients of 1 or -1, it's okay to switch to elimination or graphing when you are down to 2 variables to continue solving the system. Just don't forget to go back and solve for all of the original variables. And when in doubt, use the method that you feel the most comfortable with and that in your experience you are most likely to get correct. Don't feel like just because it meets one of these other conditions, so maybe you're not feeling particularly comfortable with elimination, but you do feel comfortable with substitution. If you're not sure, use substitution, even if maybe it's a little longer and more tedious. If you feel more comfortable with the method and you are less, that means you are less likely to make a mistake in the procedure, and therefore you are more likely to get the problem right. To get good practice with all of these, I strongly encourage my students to practice all of the methods so that they feel equally comfortable with all of them, and check your answers. So with different methods. So solve it by substitution and then solve it by elimination and see if you get the same answer. Or solve it by elimination and then solve it by graphing and see if you get the same answer. That way you have opportunities to practice, and if one of your solutions is different than the other one, it could be that there's just a mistake and you can try to track down that mistake. And so you'll learn more about sort of the places where you might make errors and where you need to be even more especially careful.